Hello, I'm not sure if it's Shongwa or Kale that are supposed to talk, but you are both muted, so we can't hear anything.
I hope it's Songwa who's going to talk.
Wow, now. I'm glad you mentioned it. Otherwise, I'll be talking for a few hours without you hearing anything. Sorry about that. So, I just wanted to review this mini grid for example. So this is an example where you have two terminal states, A with -10 and D with +10. So your goal is to get to the D state as soon as possible. So for the first, we do policy iteration. So first we do policy evaluation starting from a random policy, because the agent is just born. It's a newborn baby, doesn't know anything. So we just try the random policy. So the backup diagram, whoa. The backup diagram has a branching factor of 4 from a state because it has 4 choices, each with a 25% probability of taking one of the 4 actions. So this is a branching factor of 4 corresponding to the 4 actions. And then the environment is deterministic. So the branching factor for the environment is 1. And so based on the Bellman equation, we write out the value function for any state. Say state C is the expectation over the Q action value functions with a probability distribution of 0.25 each. So this corresponds to the branching factor of 4. Therefore, you have 4 terms in the V expressed in Q's. And then the environment is deterministic. So the environment branching factor is 1 corresponds to the Q having only 1 term for each Q value function. So, and then you solve the set of equations to get the solution for the value functions. And then you perform policy improvement. That is, you take an argmax of the action among the 4 actions that maximizes the Q value function. So notice I put these numbers as light in the light color because now they're invalid for the new policy. This is only for the old random policy. So you need to update these value function estimates to the new estimates by writing out the equations and solving for the value functions. You have the 3 new estimates now. Now, because you have a deterministic policy, the branching factor is the 1. So this corresponds to the V having, each V is expressed in only 1 Q value function. So from C, you only have 1 choice of going right. From B, you only have 1 choice of going right. So this is 1 branching factor for action selection. And it's deterministic environment, so you of course you have 1 branching factor for the Q value expressed in V. So if you are in state E and you go up, then you have only 1 choice, only 1 possibility of landing in state C. So after you update the new value functions, you do policy improvement by taking argmax over the 4 actions. And now the policies do not change anymore. It's now stable. So these value functions stay valid because the policy did not change. Even if you do another round of policy evaluation, they'll stay the same. So for stochastic environment, the difference now is the branching factor from an action node to a next level of state. So the branching factor from a state to a state action node stays at 4. So which means that for each value function, V value function, it's expressed as a average expectation of the 4 Q value functions. Whereas the branching factor of 3 from an action node means that for each of the Q value function, it's a weighted combination expectation over the 3 possible outcomes for taking that action. So if you are in state C, you try to go left. There's an 80% chance that you will land in B, 10% chance of landing in A, and 10% chance of landing in E. So similarly for V pi B and V pi E. So the first expectation taken over here, this is the expectation over the action selection, action choices by the agent. So the agent, by his own decision, may choose to go in each one of the 4 directions, upper, up, down, left, right, with 25% probability. This is under agent's control. This is the first expectation. This guy. The second expectation is the environment's control. This branching factor of 3 is determined by the environment. So environment says, okay, you want to go left? Now, I'll let you go left with 80% probability, but you may go in the other directions. You may go up or down, each with 10% probability, because the environment is windy or some other non-determinism. So you can see that these 2 expectations are really due to different causes. So this is the policy evaluation of a random policy for a non-deterministic environment, where you take expectations at both levels. Now, policy improvement, you take the argmax over the 4 possible actions from every state, and take the action that gives you the best Q value. So the decision now is to go up, go right from C, go right from B, and go up from E. So now the original old value functions are now invalid, shown in a gray font. So for the new deterministic policy, you do another policy evaluation. Now the branching factor is 1, corresponding to the 1 choice for your V expressed in Q. And the environment stays non-deterministic, so corresponding to the 3 choices for Q expressed in V. For branching factor, yeah, so Q pi is Right. So this branching factor of 3 means that, so from B, if you go right, you have 80% probability of landing in C. That corresponds to this guy. And then if you go left or right, you get blocked by the walls. So these two terms in combined lets you stay in B. So that's the second term. So this expression, this is the one step reward, and this is one choice. This is another two possibilities. So that's a total of 3 possible outcomes. So now you solve for the new value functions, you get these numbers for the new value functions. And then you do another round of policy improvement. And take argmax, you have the policies same as previous one. So now the policy is stable, so we have found the optimal policy. Now we do value iteration. So value iteration, we have the policy is computed at the very last step. In the intermediate steps, we only compute the Q star, the optimal Q value functions. So the Q star value functions are only optimal at the very end. In the intermediate iterations, it's not optimal. And intermediate iterations, the Q star, if you perform argmax on it, the policy may not be valid or may not be reasonable. So because the Q stars are not really optimal during the iteration. So we don't do the extraction of the policy in the intermediate steps. So the branching factor from a state is always 4 for the Bellman optimality equation, and you take a max. So therefore, within the expression for V, you always have 4 terms. And then for the deterministic environment, you have the same expressions for Q expressed in V. Except now it's a Q star and V star. And there's only one choice. For every action, you have only one outcome. So now you have the set of equations, but these are nonlinear equations because of the max operator. So you cannot solve them analytically. You must use value iteration to find the V stars. So value iteration. You start from values, 0 initial values, or random numbers, or some other initialization. It doesn't really matter. So you plug in 0 for the initial values and do the iteration to solve for the Q's and then the V's. Or you can do the max inside the max operator directly, so it doesn't matter. So expressing Q's is more clear. So starting from all zeros, V1C goes to 9, V1B goes to 8. Notice that you do in-place updates. So you use the current iteration's new value of V1C in the iteration for V1B. So this is the computational optimization. You don't have to do it. In-place updates are nice if you have a good choice of the update sequence. So suppose you update B or E first, then you must start V1C equals 0. Then you don't have the benefit of in-place updates. So in general, you do in-place updates starting from the positions near the ground truth. That is the positions near the external reward. For this case, B is closer to D and A. So C is closer to the external reward. So you should start from C and before update C, V1C first, and then its value can be more fresh and be used to update the other V values. So now you have the solutions, and you do another policy iteration. To plug in the previous values of 8, 9, 8 and solve for the new values, which is again 8, 9, 8. So the values have converged. So now it's converged. We can derive the optimal policy now with the arrows, with the triangle arrows, so with the argmax operator. So for stochastic environment, the branching factor on top from a state is still 4, corresponding to the 4, the max of 4, the 4 Qs, and branching factor for the from an action node to a state node is 3, corresponding to the 3 choices, 3 outcomes by taking an action from any given state. So this expression here is the same as for the policy iteration, except we have Q star and V star. So we have the 4 set of nonlinear equations, and we do policy iteration again to get these values until convergence. And you do another iteration to get updated Q values. And if you run it for several iterations, after 6 iterations with threshold condition delta less than equal to 0.01, so now you can see that these numbers 5.27 to 5.28, 6.52 and 6.53. So if you define the threshold condition to be 0.01, then it has converged. And we can derive the optimal policy from by taking the argmax on the Q star. So just to clarify, this is the process for policy iteration with deterministic environment. You first evaluate a random policy and improve the policy to be a deterministic policy, and update the value functions by policy evaluation, and then improve the policy, and then the policy has converged. So this is the for the stochastic environment, the process is similar, except yeah, it's pretty much the same, except the value function, the values are a little bit different due to the stochastic environment. For value iteration, you work out the set of nonlinear equations and just solve them recursively, iteratively. And after a few iterations, it has converged. Then you take the argmax of the Q star to get the optimal policy. Notice that you don't have the policy arrows for the intermediate iterations. And for the stochastic environment, you just do more iterations until convergence, and then extract the optimal policy with the argmax operator. So any questions? So and then we discussed value-based reinforcement learning. So first I had this analogy of computing the average expected age of a group of M students. For model-based, you first derive a model that is the proportion of students with a certain age, and then you compute the average with a simple weighted sum. For model free, you survey some random students, sample some random students, and compute the average directly. So these two approaches give you the same results for this averaging example. Their computational formulas turns out to be the same. For IR, it's analogous. So given sufficient samples, both model-based IR and model-free IR should give the same optimal solution. But in practice, model-based IR is typically more sample efficient than model-free IR, so which means that it needs fewer samples to learn a good policy. So that is for a given number of input samples, samples are state action reward pairs, tuples. So model-based IR may have converged, whereas model-free IR is still struggling. So the analogy is a little bit imperfect. So for this averaging example, these two approaches are really equivalent. But for IR, model-based learns faster. So for Monte Carlo methods, so Monte Carlo prediction just executes each episode to the end, and then estimate the v pi s, the value function for the executed policy, either as the average of the returns following the first visits to S, or every visit or following all visits to S. So for every visit Monte Carlo, instead of keeping all the sample returns in the list, like in the pseudocode, which can consume a lot of memory, we can incrementally update v pi s as a moving average with the learning rate or step size alpha with this equation. So this is a weighted sum. So more recent visits are given more weight. Whereas in the pseudocode here, this is an unweighted average. So if you write out this unweighted average in the incremental form, this alpha should be 1 over n. So alpha should be based on the number of samples you have seen. But in general, if you keep alpha constant, or you reduce it with some annealing schedule, so in general, it's a weighted sum. So actually, it's more reasonable to have a weighted sum because the more recent updates to the value function are likely to be more accurate. So So here's the computing returns for one episode. So for this episode, you have rewards of 3, 4, 7, 1, 2 with a discount factor of 0.5. And then you compute it backwards from G5 0. G5 is the terminal state, and G4 is R5 plus gamma G5, and G3 and so on. So if you expand it, you have this formula, these set of formulas. So typically working backwards is more efficient because you can reuse G5 in the G4 formula and reuse G4 in the G3 formula. But if you want to compute it forward, that's fine too. So suppose this trace contains the multiple visits to the same state. So suppose this is the same state, S1. It's visited 3 times in the trace. Then it's returned based on the first visit MC should be the value of G0. So first visit, it's hard to write with the mouse. It should be a 7 if you use first visit MC. But if you use the all visit, every visit MC, then it should be an average of 7, 8, and 2. Now you can do a equal average, just add them up and divide by 3, or you can use this formula to do a weighted average, a moving average, by giving G4 more weight and G0 less weight. Yeah, so it's reasonable because in S3 you're closer to the terminal state, so the estimation of its return should be more accurate than the previous visits. Sorry, S1, same state. So exploration, you can perform exploring starts. So in initial stage, you pick a random direction and then follow the policy. So this initial random direction gives you exploration. And for stochastic policy, you can have epsilon greedy in every step. So on policy MC control, so this is in contrast to policy iteration for known MDP, where you perform the value iteration to get the V pi until convergence, and then value improvement, value iteration, value improvement, and so on. So now for the generalized policy iteration with Monte Carlo exploring starts, you perform the policy evaluation with observed returns, and the policy is improved at all the states visited in the episode. So in a sense, it is an incomplete policy evaluation at every step. You don't do all the way to the very accurate policy evaluation. Instead, you do a halfway and just use the this return from each episode. So if you visit a certain state only once in the episode, there's no average. The average is over all visits to the same state in the same episode. And then you do a policy improvement. So here's the example where you start from the state S, and then you happen to go right to hit the goal, and then you update the value of state S. So and then you perform another round, another episode, and then update the value functions for the visited states in that episode. So after sufficient exploration, hopefully all states policies may converge to the optimal policy pi star. But if some states are not explored enough, for example, you never visited a given state, or they're only visited a few times, and the updates to Q functions is not enough to overcome the badly initialized Q init values, then their policies may not be optimal. So epsilon greedy is a popular approach for performing exploration. So we discussed this before, where you choose the greedy action with this probability, and the other actions with epsilon divided by the action selection size. So optimal epsilon soft policy is the policy with the highest value in every state among all epsilon soft policies. It's always worse than a deterministic policy. So this is generalized policy iteration with Monte Carlo epsilon soft, where you perform the policy is non-deterministic. So, therefore, this gives you exploration. So you do not need the exploring starts for exploration anymore. So on policy and off policy, on policy learns the behavior policy that's being executed. So you learn on the job, whereas off policy improves and evaluates a different target policy from the behavior policy that's used to select actions. So behavior policy may be more random and more adventurous than target policy to facilitate exploration. So it's like looking over someone's shoulder. So so notice that behavior policy must cover the target policy. Otherwise, agent will never experience the certain state action pair. So if the target policy is possible to select action A in a given state S, it must be true that in the behavior policy, it's possible to select action A in state S. So what happens if it's not true? If it's not true, then in your behavior policy, you'll never take action A from state S. Then of course, you will never learn it. You will never experience it. So you don't know if it's good or bad. So that's why the behavior policy must be more exploratory, more adventurous. That it's willing to take some very strange actions to explore the environment. So importance sampling means that if you sample, if you explore with a behavior policy, and you need to add a weighting factor to adjust it for the target policy. So I'll skip this part because I discussed it before. So in the this weighting factor rho here is computed by multiplying the probability of taking the trajectory under the target policy pi, which is probability of taking action AK from state sk. That's this pi term, your policy, and probability of going from sk AK to the next state sk plus 1. So think of the backup tree. So the first term is to start from a state node, and what's the probability of landing in the action node. And the second term is starting from an state action node, what's the probability of landing in the next state sk plus 1. So similarly, this is for the behavior policy. So and then if you perform this multiply for an episode, t is supposed the episode the length is capital T. Then starting from any intermediate step, a small t, all the way to the end of the episode, the top, the numerator is the probability of experiencing the sequence of state action reward pairs for all the steps from small t to capital T minus 1. So the multiply together is the total probability, the probability of the entire sequence of state action reward trajectory. Similarly, the denominator is the probability of the trajectory under the behavior policy. And then you notice that the environment is the same. So this latter term can be canceled out. So you only have the pi term, the policy terms left. So this is how you compute the weighting factor for importance sampling. So typically you compute it backwards from computed, let me see. Yeah, from the very last step and then backwards to the current time small t. So the difference from the off policy every visit Monte Carlo prediction for estimating the value function from the every visit on policy every visit prediction is the weighting factor for the importance sampling. And using a behavior policy for actual execution, exploration, whereas learn a target policy pi that's different from the behavior policy. So then we discuss TD learning. So this is the moving average formula. So this formula is very widely used. This just says incremental update of a value xn by taking the previous iteration x n minus 1 plus a alpha times the difference between the new estimate and the previous estimate. So if you write it out, you can see that it's a weighted sum. So the most recent value is given the highest weight. So TD learning is to perform a one-step look ahead. And so based on the Bellman equation for the value function, so V pi s is equal to expectation pi, under policy pi, the reward at the next time step plus the discount factor times the reward for the next state. So this guy is the one-step look ahead update, a one-step look ahead value function based on the next state, st plus 1. So if your v function, value function, is very accurate, then these two terms, this guy and this guy, should be equal, ideally, if the v function is accurate. But in fact, it's not equal, indicates that your value function is not accurate. So the difference is a TD error. And you must correct your value function based on the TD error so that eventually you can reduce this TD error to 0 or close to 0. So this is called your TD target. So this should be, in principle, more accurate than the current estimate of VST, because you have a concrete reward for the next step, and you have the V for the next state. So this concrete reward gives you more information. So this term, in theory, should be more accurate, and you should trust more than your current estimate. But you shouldn't throw away your old estimate as soon as a new TD target comes in, because the TD target may not be fully accurate. So you might do an incremental update, do a blend of the old estimate and a new estimate. And how much you trust your new estimate determines how large your update learning rate alpha is. If your alpha is large, say alpha equals 1, then what happens? If alpha equals 1, alpha equals 1, then you replace your old estimate with the new estimate completely. You overwrite your old estimate completely. If alpha equals 0, then you're not responsive to any new update. You keep to your old update, old value. So alpha determines how much you trust your new estimate. So the difference between the MC every visit update, which if it's on policy, you have the incremental update equation. Whereas if it's off policy Monte Carlo update with important sampling, you have the additional term of the weighting term for the given episode. And for TD, you have the on policy TD, where you perform the one-step look ahead to the TD target and then perform the update. So the difference in on policy MC is that for MC, you execute all the way to the end of the episode, and then you have the ground truth reward. you can update the value functions based on the ground truth. Whereas for on-policy TD, you are executing in the intermediate steps before the end of the episode. You don't have the ground truth. Suppose the reward only comes at the end of the episode. Then you're bootstrapping your estimate from another estimate. But of course, if the rewards are dense, that is, it's not just at the very end of the episode. You get a reward pretty often during the episode. Then on-policy TD can also learn from the ground truth pretty often. So for on-policy TD, it's the difference from on-policy is similarly it's a weighting factor for important sampling. So notice the difference here for Monte Carlo. You're multiplying the number of steps from the current time small t to the end of the episode. Whereas for the TD, you only perform the update for this current step because it's a one-step look ahead. So TD has much lower variance than Monte Carlo. So it has better convergence properties. So a tabular TD0 is just the very basic algorithm, just this formula. So bootstrapping should be bootstrapping VS from VS prime. So this is the random walk example. So this is the formula, the value Bellman equations for policy iteration, policy evaluation of a random policy. If you know the MDP, so that is the transition and reward for every action. But if you didn't know that, then you can use TD or MC to learn the value function. So the first episode is the sequence from C to D to E, and then to the end terminal state. This is the sequence. So for TD, you update the value of C by from a value of D. So you're bootstrapping. Similarly, you're bootstrapping from VE to VD, from VT to VE. So initially, every value function is 0. So the first two bootstraps did nothing. So they stay the same. The last one gets you some interesting values because now you have a ground truth reward from the outside, from the MDP. So now your value is more closer to the truth. So for MC, every visit, suppose use capital T to denote the time instant of reaching the terminal state when used as a subscript. So it's kind of an abuse of notation. So this indicates the reward at the very last step, which is 1. This is the reward of the next to last step in the episode, which is 0. So you compute the return for each state you experienced in the episode, which is all ones because there's no discount factor. Discount factor is 1. So the returns are all ones. And then you update the value functions based on this formula from return of 1, initial value of 0.5, the updated value function is 0.75 for all states. So here's the quiz. Is the following a more efficient TD update sequence with backward in-place updates? So you update VE first to be 0.75, and then you use the value of VE to update VD, kind of in-place update to get 0.625. And then you use the 0.625 to update VC to get 0.56. So it looks pretty good, right? But it doesn't work because a TD updates a VS at every single time step. It does not keep a history of the visited states. So when you are updating VC, you look at one step to see VD, but you don't see anything else because you are executing the action and you don't have any foresight. It's a one-step look ahead. Therefore, you must update VCVDV in this way. So if you executed the sequence of transitions from C to D to E, again, then you can learn. The VD can learn from VE. And if you execute it again, and the VC can learn from VD. So this propagation of knowledge is kind of incremental. Whereas for Monte Carlo, indeed, you can use the backward in-place updates, but it doesn't buy you anything. It makes no difference. If you update VE first, VD second, VC next, these values are the same because the updates are based on the returns G, not bootstrapped off the next state's value function. So in this sense, the Monte Carlo updates are more effective, more efficient than TD because you know the ground truth at the end of the episode. However, TD actually has benefits because first, you're updating on the fly, so you don't have to keep track of the history. So it's very efficient. There's no memory overhead. Second, it has lower variance updates. So that is for Monte Carlo, if you execute very long episodes for a complex game, then perhaps across different episodes, the value functions, the G, the returns can be wildly different. And the value function will be updated to pull to every direction dramatically. So it fluctuates a lot. It's not stable. Whereas for TD, if you only do one step look ahead, the updates are much more incremental and much more stable. So this is the next episode where you update. Now, in the next episode, you perform CDE first again, but not to the terminal. Only to here. And then D can learn from E. The 0.75 from the previous iterations of VE can now be used to update VD to a more accurate value, but not yet to VC. But for Monte Carlo, it hasn't reached the end of the episode. By definition, it doesn't do any updates in the middle. The next is to move from E to C. So now VE is updated, bootstrapped off VD. So you're learning VE from VD. So you're updating VE based on 6.625 from VD. So this looks strange, right? Because VE is the one that's closer to the ground truth, because VD just updated bootstrapped off VE. Now VE is bootstrapping off VD. So you're learning kind of from each other. It's a circular. In fact, it's true. So if you perform this update, in fact, it pulls the value of VE to be further away from the truth. And you're bootstrapping VD from VC. So this is again unreasonable because C doesn't know anything. C has the initial value, 0.5. It hasn't learned anything. So why would D learn from C, right? So it is true that if you perform this direction from E to D to C, you are learning from the wrong teacher. Well, that's how TD works. So similarly for Monte Carlo, this episode hasn't ended, so there's no update. So you turn around and from C to D to E, now C learns from D and D learns from E. So this is more reasonable. So you get the new values. And Monte Carlo, no update. So now I added this new transition from the last lecture. So now you move one more step to the terminal. Now in TD, VE is updated based on the terminal, the reward of 1. So now its value is closer to the ground truth of 1. For Monte Carlo, it's a little bit complex. So suppose you use every visit. Now the episode is CDEDCDDT. So I denote the first visit with C prime and D double prime. The second visit as that should be C double prime. Okay, C is visited twice. T C C D E D C. This is C. So based on the algorithm, first you update the return values G backwards to be more efficient. So because discount factor is 1, all the G's are 1. So all the returns from all the states are equal to 1. Now, based on the return, you update the value functions. So for the first visit to state C, you have this update with target of 1. First visit to D, this is first visit to C. First visit to D, first visit to E. Now the second visit to D, here. You have already updated the VD once. So you use the in-place update of 0.875 as your starting point and get a new value for VD. The second visit to C, you start from the previous estimate of 0.875. And similarly for next visit to D and E. So this update is every visit because every visit to a state must contribute to the update to the value function of that state. And it's weighted in that the later visits, so this guy, VD, VE, VC, the contribution from the new value of 1 carries more weight, gives more weight than the earlier visits based on the incremental update formula. So these visits are given more weight than these visits. It's reasonable because they are closer to the end. So they are closer to the ground truth. So this figure shows the values learned after various numbers of episodes on a single run of TD. So I say TD 0 here because there are other versions of TD with TD lambda with a lambda step look ahead. So the formulas are, so TD 0 is the simplest and most widely used. So this figure shows that the state versus the value, the straight line is the ground truth. And with more iterations, you get closer and closer to the ground truth. If you have 100 episodes, you're very close to the ground truth. And the figure on the right shows that TD converges faster than Monte Carlo. So if you set the alpha, the learning rate, to be higher, so alpha equals 0.15 versus alpha equals 0.1 and 0.05, you can see that it achieves a faster convergence, but it doesn't converge to the, it has large fluctuations. So, and also the error, the vertical axis is the root mean squared error between the true value function and the value functions learned. With a large update learning rate, you have a large RMS even after many episodes. So with a smaller alpha, it's actually it converges to a smaller error after many episodes. So but it converges slower. So it's a typical result in machine learning where the learning rate, if it's too fast, it may converge to a local optimum. So this is the Monte Carlo prediction for mini grid world. You have 4 episodes. The first episode is BCD, ECD, ECA. And for every episode, you compute the return for every state. So, and then you simply average the return for each state across all the episodes to get the estimation of the value function for that state. So you can see that state A is visited only once. So it has only one term in the average. For say C is visited 4 times. So there are 4 terms in the average. So now this average is a regular average because this is averaging across different episodes. Whereas within the episode, you use the weighted, the incremental update. So now within each episode, every state is visited only once. So you do a simple average across different episodes. So due to limited sampling of only 4 episodes, the value function estimates are not accurate. For example, in B, you happen to, when you start from B, you always end in C in the 2 episodes. But when you start from E, you sometimes end up in A, which is a very bad state. So therefore, you have a pretty optimistic estimate for VB, but very pessimistic estimate for VE, just because you didn't sample enough. If you had sampled many thousands of episodes, then they'll converge to their true values. So MC learning is not very sample efficient, and value function of every state must be learned separately. So so that's why Monte Carlo prediction methods are not really used in practice. This is the TD update with the learning rate alpha equal 0.5. So you can work out the so for the first transition BCD, first episode from B to C, you're bootstrapping B from C, and from C to D, you're bootstrapping C from D, and so on. So learning is a little bit slow because you have a low learning rate, but with a 0.9, you converge faster. So for this simple scenario, a higher learning rate, in fact, if you set alpha equal 1, it'll be even faster, because this scenario is so simple that there's no global difference between global and local optima. So you can use a very fast learning rate, but for more complex problems, you need to set your learning rate carefully to avoid being trapped in the local minimum. So this is the backup diagram for Monte Carlo, where you execute all the way to the end of the episode, and then update the value functions based on the G, the return value for every state, GT is an accurate estimate of the return from every state till the end of the episode. While temporal difference learning, you are learning by bootstrapping off the next state. You only do a 1-step look ahead. So you're learning from an estimate. So dynamic programming, you are computing the value functions from a known MDP. So you're updating the value functions for every state in every step until convergence. And the exhaustive search This last one is not drawn here because it's not feasible for any realistic problem. But if you did draw it, it'll be a huge red block covering the whole tree. So let's take a 5-minute break. Any questions? So I think we'll go today to finish the value based IR today. So we may go past 4 o'clock. So for this part, let's watch my lecture from last year. Of a given node, given state, versus temporal difference learning, which is one-step sample backup, and Monte Carlo, which is multi-step sample backup. So deep backup versus shallow backup, and sample backup versus full backup. So full backup is only possible for the model when an MDP model is available. Otherwise, you can only do sample backup for model free. So here I compare MC versus TD. So TD can learn before knowing the final outcome. So it can learn online after every step. But MC must wait until end of each episode before return is known.
Could you please switch off the titles?
TD can learn without the final outcome. So it can learn from incomplete sequences. And MC can only learn from complete sequences. So incomplete, really episodes. And TD works in a continuing, that is non-terminating environment, whereas MC only works for episodic environments. MC has high variance and zero bias. So the return, the target value, the return is unbiased estimate of the value function for state ST. It converges to V pi ST even with a function approximation. And it depends on many random actions, transitions, rewards in each episode, which can be very long with many thousands of steps. So that's why it has high variance. That is across different episodes, its variance is very large. So it affects the convergence. And it's not sensitive to an issue of value, but TD has low variance because it's a one-step estimate as opposed to many steps for Monte Carlo. It has some bias. So the target is the reward plus next state value multiplied by a discount factor gamma. It's a biased estimate of V pi. It's a bootstrapping estimate, so it's not the ground truth. Therefore, TD converges to V pi ST for tabular setting, but not always with function approximation. And Monte Carlo does not exploit the Markov property, so it may be more effective in non-Markov environments, such as a partially observed MDP. TD exploits Markov property, so it does not work well for a POMDP. So next I'll discuss Sarsa and Q-learning. So TD is a model-free way to learn the value function of every state by sampling. But if you want to get the optimal policy, we need the MDP model to go from a value function to action value function Q. So the formula is this. So sum over all the next state S prime and reward to get the Q from the V. And then you can use the action selection, greedy action selection, to get the optimal policy pi. So this is greedy action selection. So Sarsa and Q-learning, they learn Q, the action value function, instead of the value function S for use in generalized policy iteration for control. So this makes action selection a model-free tool. So for this simple maze, one-dimensional grid example, each grid position has a value of associated with it. But because each position has two possible actions, left or right, so the Q, we have 8 Q values versus the 4 V values. So if you think back to the Bellman equations, TD solves the Bellman expectation equation for state value function by sampling. So because this equation has this P R S prime SA, that's the model, the MDP model. So for model-free setting, you can only evaluate this expectation with a sampling. So here, the capital S, capital R are the particular values at t plus 1 or t for state and reward. The small s and small r represents the generic variables representing the random variables. I think the conventions may be a little confusing. I think before I said capital letters are random variables and small letters are concrete variables. But in here, the small letters denote random variables, and the capital letters denote the concrete sample. So that's TD for solving the Bellman expectation equation. For the Bellman expectation equation for action value function for Q, Sarsa solves it by sampling. And you also have expected Sarsa, which also solves this middle equation by sampling. So the reason that it's by sampling is because, so you have this summation here, which is really an expectation over all next states. But you don't have this function. You don't have this P for model-free case. So what happens is that you sample many runs and collect the reward and next Q, and then you update the Q by so this RT plus 1 corresponds to this R here, and the Q corresponds to this small q pi here. So the difference here is that you removed this expectation over S prime, and you removed expectation over A prime. And then this means that you're not taking expectation analytically, as in the Bellman equation. Instead, you're computing the expectation approximately by sampling. So you're sampling many rewards and many Q value functions, and because you're running many samples, eventually, on average, their value will converge to the expectation. So it's a common trick to evaluate expectation or average by sampling. So the only difference between Sarsa and expected Sarsa is you have the sum over A prime left over in here. So for Sarsa, so for Sarsa, you are using this sample to estimate this whole thing. So you're removing the sum over A prime. But for expected Sarsa, you're keeping it. So at every state, you're evaluating the expected value of the next Q. And this capital Q is only sampling the Q pi. So are you worried that this is really model? Is this really model free? It is model free because the model is this guy, P, not the pi. The pi is known. So what's unknown is the environment's behavior, environment's response to agent's action. So the agent knows it's pi. So I may choose left with 50% probability, to the right with 50% probability. So that's agent's own choice. So pi is known, the unknown part is P. So this is still model free. And finally, for Q-learning, you're solving the optimal action value function by sampling. So now you have the max left over in the sampling equation, but you removed the environment expectation. So now the Q for next state action value function is taking a max instead of taking expectation as the expected Sarsa. So for the backup diagrams we saw before. So this is the Bellman expectation equation for V pi. So you're backing up from V pi S prime to V pi. And TD is just a sampling version of it. It samples a particular transition from S to S prime and does a backup update. For Sarsa, notice you're backing up from Q pi S prime A prime to Q pi SA. So the little blue circle is the Q node. So in this blue circle, you are starting from the earlier state S, and you're committed to action A. And you need to estimate the value of taking action A in state S. That's the action value function. And then Sarsa does this estimate. For expected Sarsa, so you're taking expectation over all A prime. And for Q learning, you're taking a max over all A prime. So also TD and Sarsa are all on policy methods. That is it always so Sarsa always takes the action A prime. But for expected Sarsa and Q-learning, they're off policy, which means that the backup. So for Q-learning, the backup is the based on the max Q S prime A prime. But the action taken for the behavior in the behavior policy may not go to that node, Q node used for backup. So you may go to another action, a double prime, not the A prime used for backing up the update. For expected Sarsa, the backup is based on expectation. So it's a blend of all the possible S prime A primes based on a probability distribution. So obviously they could be a blend of different outcomes. So it's obviously also off policy because the backup value may not correspond to any action A prime. It's just the average expectation over all possible A primes. So we had 4 Bellman equations before. Bellman optimality, we had 2 equations. Bellman expectation, we had 2 equations. But for this Bellman equation, we don't have a corresponding sampling version for it. So it's computing the V star, the optimal value function, by taking a max over all actions and taking expectation over all next state S prime. And reward plus a next optimal value function for S prime. So because of the max A in front, it's not an expectation over a distribution. So we cannot solve for V star S by sampling. Sampling only works if you have a expectation in front. So for the other, for all these 3 equations, Bellman equations, you always have an expectation over A, over S prime, over S prime, over S prime. So these can be converted into the sampling version. But if you have a max in front, you cannot do sampling-based evaluation. So for the Bellman optimality equation for action value function, you have a max inside. So this is okay because your sampling is evaluating all possible S primes. So this part is replaced by sampling. But for the inner max, you're not sampling away. You must actually examine all the possible next A primes and taking a max. And similarly for if you're not removing the sigma A prime in the expected Sarsa case, you must examine all the next A primes that take an expectation. But for Sarsa, if you remove the sum over A prime, then you simply then for Sarsa you are performing sampling-based evaluation of both the next state and the expectation over next action. So both are done by sampling. But for expected Sarsa, you're not evaluating the summation over A prime by sampling. You're only evaluating summation over S prime by sampling. But for Q-learning, for Bellman optimality equation, this part cannot be evaluated by sampling. You must actually keep the max A prime in the sampling equation. That's why for Sarsa, you have two versions. One is the sampling version, one is the expected Sarsa. But for Q-learning, you only have one version. This guy cannot be removed, the max. So any questions? So this slide is taken from David Silver's course. So this course is very good. I highly recommend it. So it just draws the diagrams, backup diagrams in a different way. Same content, exact same content. So for full backup, you have the Bellman expectation equation, and TD is a sample version of it. For policy evaluation, TD is a sampling version of policy evaluation of E pi. And Sarsa is a sampling version of Q policy evaluation for Q pi. And Q-learning is a sampling version for the optimal value, Q value, or Q star. So exact same content as my diagram here, just drawn in a different way. And also it's missing the expected Sarsa. So this just contracts Sarsa with the Q-learning. So the only difference is here. One has a max, one doesn't. So because of this difference, Q-learning is off policy. So it takes a max A among all possible actions, whereas the Sarsa is on policy. So yeah, if you notice, there's another difference here. So A prime used for updating Q must be taken. So it's assigned to A, which means that it must take action A. But there's no such term here, which means that the action taken may not correspond to the max action used for the Q update. So that's where the on policy versus off policy part is shown. So the Sarsa must take one step and use that exact action to update its Q value. Whereas for Q-learning, it uses the max among all the possible next states. And then you can take arbitrary action, actually. Here, it chooses from epsilon greedy, but you can choose a random action, a random policy. That's fine. Because your target policy is continuously being improved during Q-learning. So your behavior policy can be some random, very adventurous policy, whereas it doesn't affect your target policy. But for Sarsa, your behavior policy must be epsilon greedy or some variant. It cannot be purely random, because there's only one policy. It must continuously improve as the algorithm runs. So here just shows the target policy is taking a max in every state. So, but the behavior policy may be arbitrary. So it could be, so this seems to be epsilon greedy. That is the optimal policy, and here is moving left. But here you add a small epsilon of moving right. And similarly for every other state. So the target policy is always greedy. So this argmax means greedy. Behavior policy is more exploratory. Could be random, could be epsilon greedy, or even some arbitrary policy. And there's no need for importance sampling. So if you had one policy, then you need to have importance sampling to account for the differences between the target policy and your actually running policy. But here we actually have a different two different policies. So on the right, you see the suppose from state st plus 1, you have 3 possible actions, a prime, and one has the q value of -3, one has a 4, one has 6. So you take the max, you update the q here, update the previous q by this 6. So the other two do not matter. So expected Sarsa and Q-learning are both our policy. Expected Sarsa subsumes and generalizes Q-learning. So the targets, the difference is one is taking expectation over A prime, one is taking max. But if the target policy for expected Sarsa is greedy with epsilon equals 0, then it's exactly Q-learning, because a greedy policy pi taking expectation over a greedy policy gives you the max. That's the definition of a greedy policy. So Q-learning is just a special case of expected Sarsa. So expected Sarsa improves over Sarsa by eliminating variance due to the random selection of AT plus 1. So if you look at, let me update this statement on the relationship between expected Sarsa and Q-learning. So indeed, if you use epsilon greedy with epsilon equals 0, then this updated equation of expected Sarsa is the same as the Q-learning. Expectation over A prime is just max. However, epsilon greedy with epsilon equals 0 has no exploration. So you're always following the currently known best policy. You're not exploring unknown states, unknown actions. So in fact, that's not really good, because you're not doing exploration. We'll see an example where if you set epsilon equals 0, it won't learn the complete picture of the environment. So that's why I deleted that statement. At the backup diagrams, so Sarsa is suppose at this point it has multiple A primes. So Sarsa is evaluating the expectation over all the all the A primes by sampling, whereas expected Sarsa is taking expectation over all the possible S primes. So suppose you had 100 different choices of A primes, not S primes. So and then Sarsa may perform 1,000 samplings to get an accurate estimate of the expectation over all possible A primes. But expected Sarsa can get that value by one single expectation evaluation. So that's why Sarsa has a higher variance, whereas expected Sarsa has a higher computational overhead. Yeah. And Sarsa and Q-learning. So this is the exercise from the textbook. Suppose action selection is is greedy with epsilon equals 0. Is Q-learning exactly the same algorithm as Sarsa? Will they make exactly the same action selections and weight updates? Answer is no, because Sarsa chooses the next action A prime in S prime based on current policy, updates the Q function, whereas Q-learning first updates the Q function based on max of next Q, and then chooses the next action A prime in S prime in the next iteration, so derived from the updated Q function. So if you look back in the pseudocode for Sarsa versus Q-learning, so for Q-learning, it updates the Q and then chooses the action from the updated Q. For Sarsa, it chooses an action A prime using the old Q, and then updates to the new Q, and then commits the action based on the old Q. So even if they're both using greedy policy, not epsilon greedy, there's still this subtle difference. So if you don't think carefully, they look the same, but actually the Q update happens at different times. Of course, if epsilon is not 0, they're obviously different, because for the Q update, Q-learning always uses the max, the greedy policies Q, whereas for Sarsa, this Q here may be non-greedy due to epsilon greedy. So if epsilon is 0, then these two are the same. However, the update and action selection still are a little bit different, as I explained here. So the Sarsa chooses the action before updating the Q, whereas Q-learning updates the Q and then chooses the next action. So here's an example for TD, Sarsa, and Q-learning. So MDP with the 3 states. So I moved this example to a separate PowerPoint, which is lecture 7.2x. X stands for extra or examples. Let me go through it. Just a review of the Bellman equations. If you have a deterministic environment, you can simplify the equations to be this. Because the environment is deterministic, there's only one P RS prime that's non-zero, that's 1. The others are all 0. So you just take the next S prime. And Monte Carlo, TD, and Sarsa. So these equations, just as review. And as a special case, if you have learning rate alpha equal 1, then each update overrides the previous value in V or Q completely in every update. So it's the extreme case of more recent visits are given more weight. In fact, they're given 100% weight. So the updated equations with alpha equal 1 is simplified to this. You simply update V with the return. Update in TD, you update with the next state as the one-step look ahead. With Sarsa, you update a Q to the one-step look ahead. For Q learning, you update to this. So the target completely replaces, overwrites the old value. So I used alpha equal 1 in this example for simplicity. So here's the episodic MDP with a deterministic environment with 3 states and 2 actions at every state. Discount factor is 1, learning rate is 1, initial state is B. So if you take the A1 action from B, you go to C. And from C, you have 2 actions, one with reward 3 and one with reward 1. From D, you have 2 actions, one with reward minus 100 and one with reward 4. So, so for policy iteration, you can write out the Bellman expectation equations for deterministic environment and 2 action choices, 50% probability each. So branching factor is 2, corresponds to the 2 Q terms in here. And branching factor of 1 for deterministic environment corresponds to the 1 V term in the computing Q. So from B, if you take action A1, you get reward of 1 and go to C. If you take action A2, you get reward of 0 and go to D. Similarly for the others. So if you solve the set of linear equations, you get this solution. So V pi D is very negative because it's a random action from D. So you have half a chance, 50% chance of taking action A1 and gives you a minus 50 reward. So, but it's balanced by the other action. So your total expected value function is minus 48. So policy improvement, you take argmax to get the greedy action based on the Q value functions, so that from B, the optimal greedy action is to C. From C, greedy action is A2 going to T with reward of 3. And from D, greedy action is A2. Another round of policy evaluation. Now the branching factor is 1 now for the action choice because you have a deterministic policy. And you solve the equations to get the new value functions. So policy improvement. So here the old values are shown to be gray, indicating that they may not be valid anymore. So now you plug in the values to get this new you're taking argmax and get the greedy action based on the Q values you compute it in the policy evaluation step. It turns out these two are equal. So from B, if you go take action A1 and take action A2, you get both expected Q value of 4. So here it's 0 plus 4. Here it's 1 plus 3. So now the argmax gives you A1 or A2. They're equally good. From C, it's the same. The A2 is the greedy action. From D, A2 is the greedy action. Now do another round of policy evaluation. And you get so from B, you have 2 equally good actions. So now you take an average. In fact, you can take either one. It doesn't really make any difference. So yeah, I think this should be a branching factor of 2 in here because the policy is actually not deterministic because you have 2 equally good choices from state B. And you evaluate the value functions and turns out it's the same as the previous iteration. So you have converged. And policy improvement, you evaluate, you improve the policy and get the same policies. From B, either A1 or A2, and from C, it's A2, and from D, it's A2. So the policy has converged. So the policy iteration process has finished. So for value iteration, you work out the Bellman optimality equations, which are these. So these equations can be solved by iteration. So I won't show the detailed steps, but the table shows the evaluation steps, and it converges to 434. And then you extract the optimal policy by taking argmax, which is from A1, you can either go to A1, from B, you can either go to A1 or A2, and so on. So now let's look at sample-based methods. Assuming that the MDP is unknown, you're trying to explore and learn the optimal value or policy. So for Monte Carlo, suppose you have 3 episodes of BDT. So you're traveling from B to D to T 3 times. And then you can write the at the first episode, the return at state D is the 1-step reward plus the value of the terminal state, which is 0. So it's minus 100. And GB is 0 plus GD, since the gamma is 1, it's the same as GD. So the value function, because alpha is 1, you have this updated equation. So VB and VD are both equal to 100. So the next episode, if you repeat BDT, the computation process is exactly the same. But if you had update learning rate alpha less than 1, then the value functions will be updated more gradually. But here they're updated in one step to be the latest, to be the newest value. So additional episodes do not change anything. So now let's try another 3 episodes from D to episodes B8. I think I didn't. B to A1. To C to A2. So you're taking the upper GB. Oh, wait a minute. Did I? Oh, sorry. Right. Still the lower path, except now. Except now you are taking A2 from B. So, but from D, you're taking A2. So now all the value functions, sorry, I'm too uncareful. So this is 4. So all the value functions are 4 based on the returns of 4. And additional episodes have the same computation. So that's Monte Carlo. For TD, so suppose you initially have the BDT with the minus 100, and episode 1, VB is bootstrapped off VD. So it's 0 plus 0. And VD is bootstrapped off VT, which is minus 100. So I indicate the bootstrapping process with the arrow in the table. In the next iteration, this minus 100 has propagated from D to B. So here's an arrow in here. And VD is the same, still bootstrapped off the terminal state, still minus 100. In episode 3, the same of the process. So it has converged. So for the episodes BDT, where from D you take action A2, is similar. So initially you bootstrap VB from VD to get 0, and VD from the terminal state. I should write another column here, but yeah, to get VD is bootstrapped to 4. Reward plus. So why did I write minus? Sorry. Yeah, and it converges after 2 episodes. So for Sarsa, now the table has 4 columns because for the from B, D, and D taking A1 to T, you have at B you have two actions. At D you have two actions. So episode 1, you're bootstrapping BA2 from Q DA1. So this is the bootstrapping. And minus 100, this QDA1 is bootstrapped from the terminal state, the ground truth. In the next episode, you're bootstrapping the QBA2 from QDA1. And in the next episode, you're again bootstrapping QBA2 from QDA1. So this is the convergence after 3 episodes. Notice that QBA1 and QDA2 stay at their initial values because you never experienced these state action pairs. You have never taken the action A1 from B or the action A2 from D. So these are not yet learned. They stay at their initial values. So if you have the episode BDA2, so you are bootstrapping the QBA2 from QDA2. And again, so the convergence process is this. So in this sequence, QBA1, QDA1, these are not experienced. These state action pairs are not experienced. So they stay at their initial values. So let's look at the Q learning. For Q learning, you have, say, the 3 episodes of BD A1T. So the first update in episode 1 is to bootstrap QBA2 from max A QDA. So you're taking a max over the 2QD A1, A2 and bootstrapping QBA2 from them. Now they're both 0 because hasn't learned anything. So now for QD, you're updating it to minus 100 as before, because in the terminal state, it's always 0, taking max or not. So for episode 2, you're bootstrapping this QBA2 from QDA, the max A QDA. So you're taking the max of minus 100 and 0, and you're updating QBA2 to 0. In the third episode, it's still 0. So you can see that this minus 100 of QDA1 is not affecting QBA2 because you initialize the value functions at 0. So at position D, you know the greedy action is to take action A2 because it has a Q value of 0. So why would you take the Q value minus 100 of QDA1, action A1? So you know there's a better action from D based on the initialization. So you can the Q update safely ignores the unsafe, the bad action A1 from D. You never take it. Of course, it depends on the your initialization. So typically you should use optimistic initialization. That is to initialize all the Q values to be pretty positive and large to encourage exploration. So let's look forward.
Excuse me, could you just go back one step?
Sure.
Reward it hasn't changed for the 3 steps or for 2 steps. Like,
yes.
So shouldn't we stop, or is, I mean, how is those episodes chosen?
I will show you in a few slides. Just be patient.
Okay, thank you.
So this is another sequence of updates. From D, you take A2, and it's very similar, except now the QD-A1 is initialized to 0. But you see a better action of A2 with reward of 4, with a Q value of 4. So it'll take the max of these two and update QBA2 to be 4. So the comparisons for Monte Carlo and TD, if you always take the action A1 from D, then it'll drive VD to -100 and VB to -100. If you always take transition D, A2, it drives VD to 4 and VB to 4. And the final values of VB, VD depend on the relative execution frequencies of the 2 transitions. So if you had a less than 1 learning rate, then you will be pulled in 2 directions by the 2 possible transition sequences, and whichever pulls harder, whichever executes more frequently, pulls to its value more harder. So Sarsa is similar, except you're learning the Q values. Q learning, you're taking the max among all actions from say D. So if you're always taking action A1 with reward -100, then the Q value will not affect the QBA2. But if you take the action A2 from D, then it'll drive QBA2 to be 4. So in this case, we're using a given set of episodes to perform policy evaluation, not control. So indeed, if we consider control, for example, Sarsa or Q-learning uses epsilon greedy policy with small epsilon, then the agent will likely avoid action A1 in state D2 after taking it for the first time. So it has experienced this very painful transition with -100 reward. So it's likely not to try it again based on epsilon greedy. So let's see how Sarsa works with epsilon greedy. Suppose the episode is B, D, A1 to Chi. So D has experienced a -100 reward in the first step. So so initially, all the Q values are 0. So the agent has no preference. Epsilon greedy is just random. So after episode 1, suppose it has experienced this episode. Afterwards, you will update the Q value of B to 0, Q value of D to -100. So our initial state is B. So it suppose at state B, you have two choices. Both have Q value equals 0. So you have pretty much a random choice. And you go to D. Suppose you go to D. And in state D, the agent is likely to select action arc max, which is A2, based on epsilon greedy. Suppose epsilon is small. So the episode is BA2, DA2. And afterwards, the QBA2 is minus 100 by bootstrapping from QDA1. And QDA2 is updated, is bootstrapped from the terminal state, which is 4. So you can see there's a kind of a lagging effect. So the previous update to the QDA1 affects the current update to QBA2. So in episode 3, you again start from the initial state B. And now in B, you have 2 actions and 2 Q values. So based on epsilon greedy, you're likely to choose A1 and go to C. So C you have never experienced. So you take a random action from C. So suppose the sequence is the C. From C you take A1. Now the QC A1 is bootstrapped off the terminal state, which is 1, and QB A1 is bootstrapped from the QC A1, which is 1 plus 0. So the bootstrapping is in the visitation sequence. So if the agent visits B first, it'll bootstrap B off the current value of QCA1, QCA2, which is 0. Let me see. QCA. Oh, yeah. So this is I had one more arrow here. So yeah. So QBA1 is bootstrapped from QCA1, and QCA1 is bootstrapped from the terminal state. Now, in the 4th episode, you start from B. You compare these 2 Q values, and you're likely to choose action A1. Go to here. Suppose the episode is again BC A1 T. Oh, it's another typo. In state C, the agent is likely to choose action argmax QC A1 Oh, my computer just froze up. So it turns out if you write too many math formulas in PowerPoint, it becomes unresponsive. Come on. Okay. So from C, now you look at the QCA1, QCA2. So the argmax is A1. So suppose you use epsilon greedy, and you're likely to choose action A1 from C. So you're likely to experience the same episode again. So now you update your QBA1 from QCA1, which is 2, this bootstrap. From QCA1 is bootstrapped off the terminal state, so it stays the same as 1. So if the agent always follows the greedy action, it'll always follow the trajectory BA1, CA1, and never learn anything new. So it'll never experience the trajectories BA1, CA2, which has a higher reward of 4, or BA2, DA2, which has another high reward of 4. So it got scared when QBA2 was updated to -100 after episode 2, and never wanted to take the action A2 in state B, because it thought that the action A2 leads to a bad outcome. But in fact, it's just because you didn't explore enough. You didn't see the transition from D with action A2. So, but if it were more adventurous and tried it again, then it will likely to experience episode 5, BA2, DA2. So if you did take this episode, you will get this new QBA2 bootstrapped off of the QDA2, which is 4. And QDA2, of course, stays the same. So as you can see that in the first few episodes, QBA2 was updated to be a very minus value, -100. Because in QDA1, you had a bad experience. But in fact, QDA2 was pretty good. It's 4. But because of the update sequence, it's in sequence update. First you update QB, then a QD. This value of 4 is not propagated to QBA2 yet. So QB thinks that taking action A2 is really bad. So so it's very unlikely to try A2 again in the future. But in fact, if you had epsilon greedy, you will try it again. And you will discover that there's a pretty good sequence of actions that leads to a reward of 4, a total return of 4. So you can see the importance of exploration by selecting the non-greedy action occasionally. So any questions? So for Q learning, let's work out so the first episode, suppose it's random actions because all the Q values are 0. So you perform the first update. So QD, you take the A1 action, get -100. Notice now this minus 100 does not propagate to QBA2. QBA2 is bootstrapped of the max A, which is 0. So it pretty much ignores that bad outcome from D. So in the same iteration, QD is updated to 4. It's 4. So now from state B, the agent is equally likely to choose action A1 or A2 since both Q values are 0. So now suppose you take the action A1 and go to C, and C A1 go to T. So you update the Q values to be 1 and 1 for these two actions. And then in episode 4, this QBA1 is higher, so it's more likely to choose action argmax A1. So in D, the agent is likely to choose the argmax of action, which is A1. So now you update the Q values to be 2 and 1. So the difference from Sarsa lies in QBA2, which stays at 0 until the agent experienced episode 4, which gets updated to until experience episode 5. So it got less scared than Sarsa, where QBA2 was updated to minus 100 after episode 2. So a Q-learning agent is more likely to explore unseen states. So suppose the episode 5 is BA2, DA2. Now you can update the QBA2 from QDA2 as 4. So from this example, you can see that Q-learning, because of the update formula with a max in it, it tries to explore the unknown actions, even though from D it has seen a very bad action, but because the initialization values are 0, so it thinks there may be a better action waiting for you at D. So it's not afraid to try to go to D again. Whereas for Sarsa, as soon as it has seen this minus 100 from D, it's very scared and pretty much never tries it. And you see the a common trick in Q-learning or Sarsa is to do optimistic initialization of the Q values. So if you initialized all the Q values to be very large and positive, then it encourages exploration. So the agent, even after some Q updates, it thinks, oh, these actions I haven't tried, and their Q values look pretty good. So why don't I try those based on epsilon greedy? So the agent is more adventurous if you initialize all the Q values to be large positive values. Okay, so let's take a 5-minute break, and no, let's go forward and finish this example. hopefully not too late. So here's another example MDP, deterministic MDP with two possible actions, left and right, and one terminal state on the right. So you have this state. You can view it as a terminal state itself, or you can view it as a non-terminal state with an additional step to go to the terminal state. These two views are equivalent. So now let's work through this example first with policy iteration. So the branching factor is 2 for the two action choices. For the V equations, and branching factor is 1 for the deterministic environment. So you solve for the value functions for the random action, random policy, and you perform policy improvement to get the initial round of policies with the gray values, and then you update the values with policy evaluation, and then you perform argmax and choose the greedy action again, and then you converge. So that's a policy iteration. For value iteration, the only difference is the max. And this is a nonlinear equation, so you solve it by iteration. So first, the simple version with a single episode, 3, 2, 3, 4. So you're moving from 3 to 2, 2 to 3, 3 to 4. So for this episode, if you use Monte Carlo, every visit, so you update the G, the return, to be -1, -2, -3 for the 3 states. So the first visit is denoted 3 prime. Then you update the V forward. So this is misleading based on the episode 1. So -3 says that agent needs 3 steps to get to the terminal state, because each step gives you a reward of -1. So the agent has experienced this episode 3, 2, 4. So it thinks that it may have to move left in the first visit to state 3, and then move right, and then to 4. So in fact, it only needs 1 step by moving right in the second visit to state 3. So the first visit with a reward of -3, with a return of -3 is misleading. So that's why more recent visits are given more weight. So in the extreme case, if you use learning rate alpha = 1, then each VS is completely overwritten in each update. So we have a more correct update, a correct estimate of V3. In here, we have a learning rate of 0.5. So the first, this -3 estimate for G3 prime is pretty misleading. So for TD update, so initially bootstrap V3 off of V2. And then you bootstrap V2 off of V3. And then you bootstrap V3 out of V4. So the update sequence is this. So the arrows denote bootstrap direction, also the direction of information flow during learning. So the external source of information is V4 equals 0. So that's the external learning signal. And V2 and V3, they're learning from each other in the first 2 steps, but none of them know anything. So they are really making some not so good values. So for Sarsa, you have these columns, 6 columns for 3 states and 2 directions in every state. So from episode 1, you update. So Q3 left is bootstrapped from Q2 right, because the action sequence is Q3 left and then Q2 right. So yeah, and then Q2 right is bootstrapped from Q3 right. So this is the bootstrap sequence. There's another typo here. So this is 0 because you never experienced Q1R. So why would it be so I used the bold font to indicate the right action Q values. So for Q learning, you're bootstrapping Q3 left from the max of the 2 actions from state 2. So this is the bootstrap. And Q2 right from the max of the Q3 So now the bootstrap is from the Q3R, which is 0, and Q3 left L, which is minus 0.5, which is updated in the first step. So it's an in-place update. And Q3R is bootstrapped from the ground truth of Q4. So it's minus 0.5. So let's look at a more complex sequence of episodes. That is, you have 3 episodes of 1, 2, 3, 4, and 5 episodes of 3, 2, 1, 1, 2, 3, 4. So first, Monte Carlo. So episode 1 is 1, 2, 3, 4. So you update the return backwards to get these return values. So every step has a cost of -1, so it's pretty reasonable to have these values. So -3 indicates that from 1, the best return, the fastest way to get to the terminal state is 3 steps. And then you update the V forward based on this updated equation with alpha equal 1. So that's the first episode. And future episodes are the same. Mainly because of the alpha equal 1 learning rate. So episode 4 is a 3, 2, 2, 1, 1 left, which stays in 1, 1 right, which is here, 2 right, 3 right, 4 right. So you have taken a detour and then returned back to the terminal state. So from you denote the first visit to as the prime, 3 prime, 2 prime, 1 prime. So then you update the G, the return backwards. First, you take a look at the G3, which is -1. G2 is -2, G1 is -3. G1 prime, because if you turn left in state s equal 1, you stay in state s equal 1. You hit the wall. So it's -4. -3 at the first visit, -4, -3 at the second visit, this guy, and -4 at the first visit, because you have 1 extra step. If you go left in state s equal 1. And G2 prime is -5. G3 prime is -6. And then you update the V's forward based on the these values. So because the learning rate is alpha equal 1, the later updates overrides the previous values. Therefore, these let me see, 3, 2, 1, 1, 2, 3, sorry. So this is the final V values. And then if you repeat the other more episodes of the same sequence of visits, the updates are the same. So this is the Monte Carlo update. So if you have the same episodes, it doesn't change the result unless you have a small learning rate. Then additional episodes may change your result by influencing your old values more at every additional episode. So for TD, you have for the first episode of 1, 2, 3, 4, you have these sequence of updates. V1 bootstraps of V2, V2 bootstraps of V3, V3 bootstraps of V4. So the first episode. Second episode, another round of bootstrapping, you get these results. Third episode, you get this. Fourth episode, you get this. So you can see that the values do not converge. So if you have additional episodes of 3, 2, 1, 2, 3, 4, this sequence of visits, then V3 bootstraps of V2, which gives you a 3. So this arrow, and V2 bootstraps of V1. V1 bootstraps of itself, which goes to -4. And V1 bootstraps of V2. V2 bootstraps of V3. The new value of V3, which gives you -4. So this is the bootstrap. And the V3 bootstraps of V4, the ground truth. So that's -1. So another episode, same sequence, and you get another round of values. So if you run additional episodes, the V1 and V2 just grow more and more negative. V3 stays at -1 because even though it's updated, bootstrapped of V2 at every episode, it's again bootstrapped of V4 later. So V4 is the ground truth. So that's why it stays at -1 at the end of every episode. So a TD failed to converge. All value functions grow increasingly negative. The reason is that if you notice that there's this sequence of bootstraps, V2 and V1 and V2, they form a bootstrap dependency, a cycle of updates. This causes these two values to be increasingly negative. So it's like two students are learning from each other, copying from each other, but they never get any true reward feedback from the external teacher, which is V4. So they're just getting more wrong and more wrong. So V3 is bootstrapped of V2 when moving left, and bootstrapped of V4 when it's moving right. So even though V3 is updated to the correct V3 of -1 when it moves right at the last step, but the episode ends immediately afterwards. So V1 and V2 do not have a chance to bootstrap off of the new V3 equals -1. So V2 bootstraps off of the -3 of V3, which is bootstrapped off of previous value of V2. So the ground truth value of -1 never propagates left. So if the episode did not end immediately, but the agent moves left again after visiting state s equals 3, then V1 and V2 will have a chance to bootstrap off the new V3, and they may converge to the correct values. So in this particular sequence of sequence of visits, these two V1 and V2 are not getting any real useful learning signal from the ground truth. So they're just bootstrapping off each other and learning the wrong values. So for Sarsa, the first 3 episodes, these episodes so the first episodes are updating the right Q values, because you're only moving right, you never experience the moving left. So the sequence of updates are these. So these look pretty reasonable, because you're following a straight path to the goal, to the terminal state. So Q1R is -3. Indeed, from Q1 you should move right, and it should take you 3 steps to get to the terminal state. So for the episode 4, the roundabout episode, this episode. So now Q3 left bootstraps off of Q2 left. This guy. Q2 left bootstraps off Q1 left. Q1 left bootstraps off itself. No, bootstraps off of Q1 right. So it is itself, but because the next action is to go right, so it bootstraps off of Q1 right. Q1 right bootstraps off of Q2 right. Q1 right, this guy. This is the -3. And Q2 right bootstraps off Q3 right. This guy. Episode 4. So sorry, it's the previous, but it's the same arrows. Yeah. So episode 4. This is the sequence of updates we're discussing here. So episode 5, the update sequence is the same. But the values change, and so on. So after episode 8, the values have converged. So so now you can see a sequence of the red arrows indicate a stable set of dependencies that keep the Q values stable after episode 6. So for Sarsa, you can see that after convergence, these 3 Q values look very reasonable. So they are indeed based on the shortest path to go to the terminal state. But moving left, these action values are not very reasonable. So this is because the only trajectory with moving left actions are this roundabout sequence you have seen. So, and the Q values are updated based on only this episode. It's on policy learning. So anything it has not experienced, it has not learned. So from state 3 taking action left, it can only take the above trajectory and reach the goal in 6 steps. Hence, Q3 left is -6. So if you had collected more trajectories like 3, 2, 3, 4, like this, then Sarsa could learn the more accurate Q value of -3. So if you go left from state 3, you can immediately turn right from state 2 and reach the goal in a total of 3 steps. So you can see that on policy learning has this drawback or characteristic that anything it has not experienced, it will not learn anything about. Even though from state 3, it has turned right once from the episode, but because the entire trajectory is going left, this roundabout trajectory, it only knows this trajectory. It doesn't know anything else. However, the argmax, the actions are still correct because the right action is always better than the left. So this shows that policy often stabilizes long before the value functions converge. So why Sarsa converges? It's because the bootstrap dependency is this dependency. So so Q3 left in the reverse arrow direction, Q2 left, Q1 left, Q1 right, Q2 right, Q3 right. So this is not a cycle. So even though you started from 3 and ended at 4, the first is to Q3 left. The second visit is Q3 right. So these are two different nodes. And similarly for Q2. So there's no cycle of dependencies that caused the value not to converge for TD learning. TD only has one V for every node, whereas Sarsa has 2 Q values for every node. So this bootstrap dependency chain determines the stable values for the Q values, not a cycle. So for Q learning, the first sequence of updates for the straight line episode is this. So the Q3 R has a -1, but the -1 does not propagate to the left because you take the max value. So every time you see the -1 is overshadowed, it's dominated by the 0 of Q3 left. So it's kind of optimistic Q value initialization. So the S equal 2, you think that from 3 there's a better action with a higher Q value of 0. So you disregard the -1 of Q3 right. So for episodes 4 to 6, you perform the bootstrap Q3 left bootstraps of Q2. The Q2, the max of Q2 values is 0. So this is -1 for Q3 left. And Q2 left bootstraps of Q1. The max of these two is 0. So this is -1 for Q2 left. Q1 left bootstraps of the max of these two Q values, which is 0. So this is bootstrapping of itself. And Q1 right bootstraps of Q2, the max of these two is -1. So it's -2 here. And Q2 right is this. So the sequence of updates from episode 4 to 6 gets you these values. And then additional episode 7 gets you these values. And then after episode 7, it has converged. So the red arrows indicate the set of dependencies that determine these stable values.
Just one thing. You are using red color to indicate change, isn't it?
Yes. The red.
Yes, episode 4, in that case, in middle, you have two, should have two reds, -1 and -2.
I'm sorry, which shouldn't be read?
Episode 4 in the middle, -1 and -2.
Here. Yeah, sorry. These two should be read. Good catch. So for Q learning, the Q value converges and all the state action values look very reasonable. So first, these three are reasonable. So the optimal path can be derived from the bootstrap dependency chain. So bootstrap dependency chain Q1 right, bootstraps of Q2 right, Q1 right, Q2 right. So this dependency, this is the reverse of the arrow direction, and Q2 right to Q3 right. So this is actually the shortest path, the optimal path. By moving right from state Q of state 1, and Q1 left is -4. So if you move left in state 1, the dependency chain, bootstrap dependency chain corresponds to the optimal path 1, 1, 2, 3, 4. Because from 1, if you go left, you stay in 1 for 1 step. And Q2 left is -4. So from Q2 left, you go left 1 step, and then you go right. So that's 4 steps to the terminal state. Q3 left is 3 because go left, and then right, and then right. So that's 3 steps. So you can see Q learning is smarter than Sarsa. So since it's off policy, agents can learn the correct Q values that correspond to trajectories that it has never experienced. So for example, the agent moves left in state 3, even though it has never experienced the trajectory 3, 2, 3, 4, the bootstrap dependency Q3 left bootstraps off of Q2 right leads to that trajectory instead of the experienced trajectory 3, 2, 1, 1, 2, 3, 4. So let's see. So agent moves left in state 3. So you can see that bootstrap dependency from the initial episodes, the first episode 4, when when agent moves left first in state 3, the bootstrap dependency is this. So it bootstraps off of Q2 left because it has never experienced. Well, it doesn't have enough experience. So it thinks Q2 left is perhaps better than Q2 right based on the Q values at episode 4. In fact, based on the Q values of episode 3. So its bootstraps off of Q2 left is 0. Q2 right, you have experienced once. It has a value of -1. So the Q3 moving left thinks, okay, left is perhaps better from state 2 because it has a higher Q value. So, but gradually, as it goes more and more episodes, the Q values of these Q1 and Q2, especially Q2 left, are growing more and more negative because they're not because the value propagation from the ground truth is slow, so it hasn't reached the Q1 and Q2 yet after these episodes 4, 5, and so on. So they grow more and more negative until at this point, episode 6. Now the bootstrap dependency is no longer Q3 left, is no longer bootstrapping off of Q2 left, but from Q2 right. It has changed to here. So this shows that Q2 right from a previous episode, from this kind of episodes, the roundabout episodes, from state 2, you know that you can reach the goal in 2 steps. That's why you have this Q value of -2. Now, as the episodes evolve from stage 3, if you go left, initially, you haven't learned enough. So you think that from 2 going left is better. It has a higher Q value. But as you go learn more and more, you realize that, agent realizes that actually going right from state s equal 2 is better after episode 6. So the Q3 left will bootstrap off of Q2 right instead of Q2 left. So that's how it learned this path 3, 2, 4, even though it has never experienced 3, 2, 4 ever before, thanks to the max operator in Q learning. So that is in Q learning, because of the max operator, you can learn from previous experiences that contributed to the Q value of a given state, even though therefore causing the agent to follow some brand new trajectories based on the Q values, even though these new trajectories like 3, 2, 4 was never experienced in the actual episodes. Okay, that's the end of today's lecture. Any questions? So we have a few classes left. So I will finish value-based IR. I still have a part on the function approximation, which I'll finish, and also for the policy-based IR, these two should be finished next class. So for the exam, I will cover all the lectures before 7.2x. That is up to the value-based IR section chapter. And the rest, I will try to cover as much as possible, but lecture 7.3 and 4 and 8 would be for your entertainment only, not covered in the exam. Okay, that's it for today. So any comments and questions?
Yeah, just for the exam, how will be the ratio with the all classes? Will it be equally distributed in the exam or?
Yeah, so for the sample exam questions, I'll pretty much give the short answer or selection questions equally distributed across different chapters. And so this is actually the MDP I discussed for the simple version of the chain example, the same exact steps. So I'm thinking giving such a question, maybe based on one of the two worked examples and with some minor tweaks. So if you understand this lecture, you shouldn't have any problems.
Okay.
I have another question regarding exam day.
Sure.
There is both lecture and exam in the same day in the schedule.
What exam?
Exam day. There are two. Like, let's see, just a second. We have lecture at 2 o'clock, and then we have exam at 5:30.
Oh, so the lecture I was thinking that. So next week we have the lecture is supposed to let me see. Oh, okay. So we only have 2 classes left. Okay.
My question is whether, I mean, it's not. I would like to learn more, but I don't think it's like appropriate to have both lecture and exam after and directly after the same day.
Yeah, so I had a announcement that the Monday's lecture time is really used for the Q&A. So yeah, we'll have a Q&A session on Monday, 14 to 16. So I wasn't planning on giving a real lecture on that day.
Okay. Yeah.
Yeah.
Generally, I mean, it's like have a lecture and exam on the same day. It's not, even if it's question and answer. But okay.
Yeah, it'll be a kind of a more informal session. We can have kind of any informal discussions you wanted to have, and including any questions on the lecture material or anything else. I'm a little afraid that no one will ask any questions. We'll just sit there. So we'll see what happens.
That's the risk, because I mean, I would prefer to use that time actually to learn, to read some more before the exam. So it's like it's not so lucky to have it the same day. So I would prefer it to either move it maybe day after or some other day.
Yeah. So in my in the lecture schedule, actually I think I won't have time to cover lecture 8. So lecture 8 is named imitation learning, but it's actually more than that. So it covers the actual applications of imitation learning and reinforcement learning on the autonomous driving. So it's mainly a discussion of a lot of research papers. So in this, if you're really if you're really eager to learn, you can watch my lectures from 2020, which is lecture 6 and 7.
Yeah, so I'll probably do it, but I'm just saying I would prefer this last lecture, question and answers, that you move it to some maybe just that day after, not to have it same day, because probably I won't participate because I will use that time to just prepare for the exam.
Okay.
Very few persons will are going to participate, so we just wait for them.
So so you're saying that we should have a lecture after the exam on some topics that hello, someone is
Or just the question and answers if you want, but not the same.
okay. So let me see.
I mean, that's my suggestion. I'm not sure how others are going to react. So, but I would prefer not to have it same day, because probably I won't participate.
Yeah. So Q&A. So should I have it on the same day, or should I maybe do it? Okay. Because I know that some students are working, so they may not have time to watch the live lecture during the daytime. If they usually watch the replay, if I have the lecture on the same day afternoon, they won't have a chance to watch the replay. So it wouldn't be very fair, even though it's a Q&A session. So
It's absolutely up to you. I mean, personally, I'm pretty sure that I will use that time just to read some more like final preparation for the exam. So yeah, I won't just sit and listen to question and answers.
So Demir asks, can I put all the course material on GitHub? So they are, isn't it? Oh, okay. A few assignments, maybe not. So why can't you reach a Canvas? Okay, I'll discuss with you later. So for the lecture, I think, how about this? We'll change the lecture on Monday to Sunday. Is that good? Okay, let me think. So yeah, let's have a Q&A on Sunday, so at least you have some more time to reflect and study the material before the exam.
That worked for me.
Yeah. Okay. Let's do that. I'll send out the announcement.
Okay. Thank you.
So for Demir's question, he said he can't see material on Canvas. So pretty much all the material except the lecture videos are on my GitHub. So I don't know what else you need. So so why don't you send me an email and as to the exact materials that you're requesting access to, and I'll see if I can put it on GitHub, but not the videos. They're too big. Okay. Let's see. It's pretty late. Thank you for sticking for so long. And goodbye.
Thank you and goodbye.
Yeah.